Hi, this is Dr. Anthony Revis, and this is Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis, Chapter 2, Polymeric Materials. Polymers may be solids, viscous fluids, rubbery or elastic, or stretchable based upon their physical state and physical properties. In other words, depending on the physical state or the physical properties of the polymer, you will get either a solid, you'll get a viscous fluid, or you might get a rubbery, elastic, or stretchable material. Okay? Now, solid polymers may be either partially crystalline or amorphous. So if you have a solid polymer, they'll fall in the category of either partially crystalline or amorphous. In other words, it'll have some crystallinity in it, or it'll be amorphous. So what's an amorphous polymer? Amorphous polymers have random structures that do not exhibit any crystalline structures when they're measured. So when you measure it, you don't find any crystallinity in it. Okay? In other words, crystals, exactly what you're thinking, they have this well-defined structure. So amorphous does not have this well-defined structure. Okay? Amorphous polymers are less rigid with no clear melting point, but they have a glass transition temperature. In other words, they have a temperature over which the material becomes glassy, and that mimics or approximates a melting point, but it's really not a melting point. But some will call it a melting point, but it really is a glass transition temperature. Okay. Amorphous polymers are transparent. That's why actually they make good polymers for when you want to be able to see things. Okay, so that's what an amorphous polymer is. All right, it's a random structure, no clear melting point, it's less rigid, and it tends to be transparent. On the other hand, crystalline polymers are generally very ordered and show crystallinity when they're measured. In other words, they have a crystalline behavior to them when you measure its properties. Now, that's pretty important to why it functions the way it functions, because crystallinity gives them strength and rigidity. So crystalline polymers tend to be they have more strength, and they're more rigid. They have a clear they result in a clear material at the melting point. In other words, you can clearly see that that's a clear melting point. All right, and when it suddenly becomes a liquid like other melting points in like solids, it just is there. You see the solid, all of a sudden, wow, it's a clear liquid. Unlike amorphous, it has a glass transition point that's longer until it's all liquid. So a crystalline material become liquid much faster. So crystal structures are generally opaque because they reflect light. So if it's reflecting light, it probably has some crystallinity in it. And so that's what I'm going to do. You look at it and say, is it reflecting light? Yes, probably has crystallinity. Is it reflecting light? No. It probably doesn't have much crystallinity, and it's probably more amorphous. And these are ways we differentiate these two materials. The random material, which is amorphous, the more structured and ordered material, which is crystalline. Okay? Now, polymers may be grouped by the difference in the orientation of the repeating units in the backbone as well. So this is one way we can start to differentiate the polymers based on the chain orientation. Tacticity describes that repeating pattern of the attached groups. So you look at the attached groups, you look at the repeat units, at least the repeating pattern of the functionality on the polymer, and you determine whether it's one of three categories. Isotactic, you have all repeating units on the same side. Straightforward. If they're all on the same side, don't second guess it. It is called isotactic. That is the definition. That is the word. That's what it's called. Synotactic, on the other hand, alternates units across the chain in an ordered fashion. Okay. front, back, left, right, etc. So it alternates. And when it's alternating, that's called syneotactic. And then you have atactic, which is more random. It's just disordered. You can't find a unique pattern to it within some reasonable number of repeat units. That's called atactic, and it's random. And if it's isotactic, it has one set of properties. If it's syneotactic, it has another set of properties. If it's atactic, it has yet another set of physical properties. And so by looking at the physical properties, we can often decide whether or not, or at least guess or hypothesize whether or not it's atactic, syneotactic, and isotactic. And that is something that you will want to learn how to do in this course. Okay, how to differentiate isotactic, syneotactic, and atactic. Isotactic, all the units on one side. Syneotactic, ordered, alternating. Random would be for the atactic. Okay, where there's no particular order to the units. There's one way to classify polymers, is again by the tacticity. Now, polymers may be grouped also as fibers, plastics, coatings, adhesives, sealants, and others based on the application. So what are we going to use them for? Where do they have application? All right. Why do we manufacture them? That's called the in-use property. All right. And there's three main in-use properties that we consider when we look at these. One of those in-use properties that we look at is whether or not to classify this is whether or not it's a thermoplastic. Is it going to be used as a thermoplastic? Okay. All right. What are you going to use it for? Is it going to be is it a thermoplastic? Okay. So a thermoplastic softens and flows upon heating. So you have this solid polymer and it's softened and it flows upon heating. That's going to be a thermoplastic. They're solids at room temperature and can be shaped when melted and then become rigid upon cooling. So you have this solid polymer, you heat it, it melts, it forms a shape, and when it solidifies, you have this solid material. And that's called a thermoplastic. Okay? A thermoset, however, okay, these thermosets, they have irreversible shapes once heated for the first time. Once you heat them, that's it. These are what's called partially polymerized raw materials. Now, you say, wait a minute, you're talking about the first was a thermoplastic polymer, and now you're talking about partial polymerized. In other words, when we talk about partial polymerized, it means that it is not at the polymer molecular weight of its final in use. Okay? All right, it is a polymer, but it does not have the final in use molecular weight or molar mass. By the way, you will hear me use molar mass and molecular weight interchangeably. Be aware of that. So, thermosets are partially polymerized as raw polymer, but will cure cross-link during the heating process. So during the heating, they have this this ability, right, to be partially polymerized. You heat it up, and then it gets its final shape when it's cured or cross-linked. And what does that mean? Take a look at the diagram. A thermoplastic will have chains, okay, that run as shown here. And between these chains are no cross-links. They're just chains that are interacting openly, no covalent bonding across the chain networks. However, in a thermoset, there will be cross-links across the polymer chains. So you have this polymer chains running in the direction. Okay, so it's like a train track that doesn't have the wood ties across it for a thermoplastic. So it just has the railroad tracks running, but there are no ties. Then the thermosets will come across and put the ties in it. Okay, And so that is the difference. And we show you some different names and types of polymers that are thermoplastics. And you do well to memorize these or learn them in some way. You have polyethylene, polypropylene, polystyrene, PVC, which is polyvinyl chloride, and then you have a couple of the Perspect and nylon trade names here as well, brand names as well. And then you see the ones for the thermal sets, the phenolic resins, the epoxies, which is like the hardener glue, polyurethanes, polyesters, and silicones would be for thermal sets. So these are different types of polymers, and the thermoplastics and the thermal sets have different in-use properties that allow them to be formed into in-use products. Okay? All right? So be aware of that. All right. Now, another polymer that we look at, or another way of categorizing these based upon in-use properties, is by an elastomer. Again, you have the thermoplastics, you have the thermal sets, that's two, and the third one is elastomers. So elastomers are just that. They show elastic behavior. They undergo elongation, usually stretched as many as 500,000 times the original shape, and it bounces back. It's like pulling a balloon. It's elastic. Pulling a rubber band. It's elastic. It always pops back to its original shape. Okay? Elastomer polymer chains are held together by weak intermolecular bonds that have properties that allow them to stretch and pop back even under mild conditions. Okay, you can stretch them, and the polymer chains move across each other even under mild conditions. And that's what gives it its elastic material. Again, the polymer chains stretch even under mild conditions, and that gives it its elastic property. Okay. Some example would be natural rubber, neoprene, silicone, polyurethane, rubber, and elastomers. So you see, you have thermal sets and thermoplastics again, and you have the elastomers as well. And you know here that the elastomer examples that I just used are thermal set elastomers. And we know the thermal set elastomer has an irreversible shape once it's put there. For example, if you use a silicone caulking, once you put it on the bathtub, it gets its shape, it seals, it cures. That's it. Similar with polyurethane and other rubbers. Some of the applications, motor vehicle applications are very are used extensively. I'm sorry, let me say that again. Elastomers are used extensively for motor vehicle applications. Then we have a number of consumer products, construction industry, industrial products, wiring and cable, and medical devices alike. Many of them will fall within the elastomer. Okay, based upon again their in-use properties. Okay. Now, one of the features that helps these polymers to be useful for their in-use application is the type of polymer used based upon its monomer distribution. So in other words, how those monomers are distributed helps impart certain features to polymers. Okay? So polymers may be classified then as homopolymers and copolymers. Okay? So you can have a homopolymer or you can have a copolymer, and you can guess by the names right away what that means. Yeah, you get it? Homopolymers are single monomers in the polymer chain. So all you have is AAAA, or it could have been a BBBB or XXXX, but it's all the same. It's homogeneous in terms of its monomer distribution. Okay? A copolymer, on the other hand, has more than one monomer in the polymer chain. The polymerization of different monomers, at least two different monomers, gives it to you. So you have an AB, 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 or some random distribution of that, but you'll be able to identify at least two polymer monomer units in the polymer chain. Now, the properties and performance of the polymer is often influenced by whether it is homopolymer or a copolymer. And what polymer chemists have learned to do, what polymer chemists have learned to do, is how to choose whether or not it should be a homopolymer or a copolymer. And there's a lot of science that goes into that, some of which will be taught in this particular short course. So homopolymer and copolymers are an important feature. Okay. However, we will not go into much of the depth of how we make a lot of these how we make them and how we use a lot of them. The scope will be limited to a select number of homopolymers and a select number of copolymers. But keep in mind, the industry is full of both types of polymers, and they have great value to the industry and to end-use applications. So, polymers are classified by the order and organization of the monomers. Two or more monomers are known, again, as a copolymer. So the homopolymer, let's take a look then. You could have AAA or BBB or CCC. Then you might have what's called block copolymers, in which you would have the monomer units of A together and the monomer units of B together. That would be called a block copolymer. These are terms that you do well to memorize. Then we have alternating copolymers. You'd have AB, AB, AB in an ordered fashion, in a predictable fashion. And then you could have random copolymers of A, BB, AB, AAB, some random distribution that is not as uniform. Okay? And you can further have what's called a graph copolymer, where you have a chain of A's to which a B chain of polymers has been grafted. Each of these has its own unique features. What determines the feature, which feature wins, is the end-use application. And in some cases, several types of these might be tried on an end-use application, and the winner is the one that met what the customer wanted. That's the final decision in terms of which of these is used is based upon the meeting the customer's needs or some end-use need. So polymer development is very practical in that regard. It considers the end-use need or application very critical in its deliberation. Okay. Now, to make these polymers, whether they are homopolymers or copolymers, we need monomers. We get these monomers from primarily the fossil fuel industry. We take them as a distilled fraction from the top of the distillation tower, about 7 gallons per every 55-gallon drum. So these are examples of what the monomer would look like and what the polymer would look like. How we name the monomer and how we name the polymer. Okay? The first four on this slide are homopolymers. The first one being ethylene, which is polymerized into polyethylene. Vinyl chloride, which is polymerized into polyvinyl chloride, or PVC. Ethylene oxide, which is polymerized into polyvinyl alcohol, PVA. Or we could take ethylene glycol and polymerize it into polyvinyl alcohol, PVA. Oftentimes, the one that's used depends on how number one, the raw material that's available, and the other is how the manufacturing process is designed. And then a third feature, frankly, is what you want your catalyst to be, and essentially what other raw materials you might use to get to the end-use product. But in the end, once you get to the polymer, in general, if they have similar molecular weight or molecular weights close enough, oftentimes either process will work for the end-use application. But some end-use applications are so narrow focused and so precise till it requires to match the process to give you the output polymer for the end-use application. And then we have bisphenol A, which has fallen under much scrutiny because it tends to have some toxicity issues with it, particularly in using in baby nipples, baby pacifier nipples, and baby bottle nipples. So bisphenol A with phosgene gives us polycarbonate as a copolymer. Okay, so we have a copolymer. So polycarbonate is a copolymer of bisphenol A and phosgene, shown here. Now, not only are the monomer units important in polymerization, but how these monomer units are attached is very important to developing different types of polymers with different features, which means they have different performance values to the industry, which means they're formed into different types of products. Okay? So let's look at these examples. Shown here are 4 examples: linear, branch, star, and rake. In the case of linear, it's exactly what it says. It's linear. No branches at all. Okay? It's just a straight chain polymer. That's it. Branched looks like it says. It has branches. But these branches tend to be somewhat random and not necessarily uniform, and therefore it's just simply called branched. Now, a star polymer is a type of branch polymer, but it has a very unique branch where it has these 4 polymer chains coming from a single carbon, or not only a single carbon, but a single hub, if you will. So that hub could be a carbon, or it could be another polymer that serves as a branching unit, or branching serves for because of its branching functionality. But these will be star. They'll have essentially 4 or some number of polymers coming from a single hub or a single source. And then rake will have a linear polymer, to which several other linear polymers are coming off the main backbone to form a rake structure. Okay. Many of these will be in the form of thermoplastics. So thermoplastics soften at temperature, harden when cooled, and these are thermoplastics, so you can repeat it. So you can heat it up. You missed it, or you took a nap, or something happened and you forgot to pour it, or whatever. You can repeat it. And these are examples of these thermoplastics: HDPE, LDPE, polypropylene, polystyrene, PVC, and PETE. And this comprises about 75% of the world's usage. So you're looking at structures of these structures here in the form of these polymers, HDPE, LDPE, and etc., form about 75% of the world's usage. So if you can do these polymers, you can make a pretty good living and make impact in the market. 75% of the world's usage comes from these 1, 2, 3, 4, 5, 6 polymers shown here. You do well to remember those. You can also have what's called a network structure or a ladder structure. The network simply is that. It is a network of polymers intertwined in some fashion with many cross-links and many bridges. Some will be a star-type bridge, some will be other type, rake-type bridge, branch-type bridges, but bridges across it forms this intertwining network. And because of that, there are these features that it also imparts to the final in-use product. And then we have the ladder, which has two linear chains that are cross-linked across to give you this particular structure. Okay, and many of them will show up as thermoset. They harden, or it hardens or sets up and strengthens at temperature. So you heat it so that it can get its final strength, and once it does that, that's it. Cannot be reheated at all. These will be resins, polyesters, epoxies, and phenolics. Epoxy and phenolics are used a lot in areas where you need something tough and hard. So you have a lot of these epoxies, so you have the epoxy glues, and they're really kind of hard. And you have these nails that people put on and things of that nature. Many of those are epoxy types and phenolics. And then you have these polyesters and resins. They tend to be really kind of tough and can resist scuff, which is why polyesters are used in many of the areas where they find really good application. Okay, so that would be based upon, again, the polymer architecture helps to define how we can use these polymers. So what are some of the commercial applications? This slide shows you commercial applications of these polymers that are leading this 75% of the market. PET or PETE, food and beverage, shampoo, body wash, cleanser bottles, and things of that nature. And then you'll also have PET for soft drink bottles as well. You should probably think about that or add it to the list. Oh, we did say beverage. So yeah, beverage. There you go. Soft drink bottles there. And then we have high density polyethylene. Then later on you'll see low density polyethylene. But high density polyethylene, bottles, sheet, film, drum, pipes, conduits, a little tough material, cable insulation. And then let's just drop down to low density polyethylene and compare it. You have packaging film, toys, flexible bottles, coatings, houseware, wires, and cables. That's what these will make up. Okay, and then we have polyvinyl chloride, PVC, construction, rigid pipes, film, and this has chlorine in it as PVC, polyvinyl chloride. Then we have polypropylene, automotive parts, a lot of automotive industry parts for polypropylene, and then polystyrene, packaging, appliances, insulation, toys, houseware. Many of these you see around. You see polystyrene quite a bit, and we sometimes don't recognize it as such because all we're looking for is the blue insulation or pink insulation on the homes. Now, each of these polymers, okay, has a recycling code associated with it. The first one, PET and PETE, is a one recycling code, and you'll learn more about how to use these recycling codes. There's an appendix to this that shows a list of many of the polymers and what their recycling codes are. This helps to decide whether or not they can be reused, how can they be reused, and how to sort them in recycling. For example, PVC should always be sorted separately. It should be put in a separate recycling bin because it has chlorine in it, which is rated at 3. And its rating of 3 tells them that it should be segregated from many of the other plastics because the chlorine in there, it can't be recycled by the same processes of some of the others. It can't be reused by some the others. So oftentimes, if PVC contaminates a load of plastics, it all goes to the landfill instead of going to the recycling because it can't, because the chlorine that comes from burning it, or oftentimes when it's degraded, that is liberated. It's liberated from it, can cause problems environmentally and health wise. But in the application where it's used, it finds really good, has really good utility. So these are the different codes. You do well to memorize them and learn these codes associated with each of the polymers. They are all unique, and this is what helps to decide how they should be recycled. Now, where do we get these from? We get these from monomers, which are polymerized into oligomers, which are further polymerized into full polymers. Monomers are small molecules used to synthesize polymers. Monomers are the raw materials of the polymer. We take that raw material. And then we polymerize it in the intermediate stage of what we call oligomers. These are small polymers. They're not full grown yet. They're not as large. They have a smaller number of polymer units. But if you continue to polymerize that oligomer or add monomer units to it, you will get the polymer. Okay, and then these polymers are further cross-linked, and we get the thermosets, we get the thermoplastics, we get the elastomers. Okay, we get all these different structures. We can get rate structures. We can get branch, linear, star structures. We can get network structures. We can get ladder structures. These are all important parts of the features. And once we get them, we put them into a recycling code so we can know how to reuse them in the environment, or whether they go to a place where they recycle or reuse, or do they go to a landfill where they stay from now and forevermore and make a big mountain made of trash. And then we take a look again at these monomers, at their distribution, and we decide whether or not they fit a homopolymer, block polymer, alternating copolymer, or random polymer, or graph polymer. That helps again to decide about its use and how we can choose it for certain applications. Now, when we look at this, where we're making these oligomers into polymers, into all these structures, homo, block, alternating, we have to analyze it in some fashion. We have to characterize it. And one of the ways we characterize this, which helps us also to classify the polymer as low molecular weight, medium molecular weight, or high molecular weight, okay, or whether it's a oligomer or a polymer, is by what's called GPC analysis, okay? Gel permeation chromatography, meaning that we have a polymer that goes through a gel, and the gel has these pores, and based upon the size, okay, it can differentiate between the size of the polymer. In other words, the gels have a certain pore size, a pore diameter that allows certain polymers to go in and certain polymers to pass over, which means that the larger polymers, okay, higher molecular weight polymers will come out of the GPC first because they don't go into the pores. You get it? There's more distance and more surface area in the pores. They run around the pores and they come out. So small ones go in, take their time, run around on the surface, while the large ones are going right across the pores and come out first. All right? And so one of the things we do to these polymers to stop them from growing is we do what's called an en bloc. En bloc helps us define where that molecular weight is going to be stopped and where we're going to terminate it. Okay? And one of the things we can use GPC for is to determine its molar mass or molecular weight based upon the N group, the N groups that we encap it or stop its growth with. Okay? So en bloc results in a shift to higher molar mass, molecular weight. Okay? And we show you an example here in ethylene glycol-based block copolymers. And we now know what copolymers are. So we take this block copolymer and we encap it with these 6 different en blocks. What we discover is that the larger the en block, hexa, the faster it elutes from the GPC, which means that it has a higher molar mass or higher molecular weight. Let's review it. In GPC, higher molar mass, higher molecular weight comes out first. Lower molecular weight comes out last. Okay? So if we en bloc this with a hexafunctional, it will elute first, penta next, tetra, tri, di, and your first basically single unit put on there will come out last. The single unit, the one to the far right, would say DIP. that's really almost like taking the 1 and putting a small unit on it. Okay, you get it? Not much there to completely en bloc. It's only partially en bloc, if you will. But when you're fully en bloc, and the higher the en bloc you put on it, the higher the molar mass of the en bloc is proportional to when it comes out of the is an indicator of when it will come out the GPC. The higher molar mass will come out the GPC first, and the lower en bloc will come out the GPC last. So this is another way of characterizing these polymers and analyzing these polymers, is to use GPC to determine its molar mass. Another way to look at GPC, okay, all right, is shown here, where we take GPC and we can determine the extent of polymerization. In this particular diagram, higher molecular weight comes out to the left side, lower to the right. To the left side of this chart means it's coming out faster. To the right side of the chart means it's coming out slower. And it's coming out slower because it goes into the pore region, interacts inside the pores, and that is a time factor, and it comes out. The higher molecular weight units do not all go into the pores. They simply go past the pores. Okay? So, GPC shifts to higher molar mass, or molecular weight, as the polymerization proceeds. And we show this as an example of an acetyl link branched polydimethyl acrylate material. So we look at it and we discover that we can follow the growth of the polymer based upon the time and its molar mass. So for example, in the first curve, we see that it takes about 10 hours for this to be about 70% complete. And we can tell that by the shift in the molar mass to the higher molecular weight, to the left side. When this was done for only 7 hours, we see only 63% completion. We get a lower molecular weight, molar mass. 3 hours, even lower molar mass. 1 hour, pretty much nothing at about 5%. So essentially, we can start to characterize, all right, and categorize these polymers based upon their extent of polymerization. The general rule of thumb is the longer the polymerization, the higher the molar mass. The shorter the polymerization, the shorter the molar mass. You get it? And we will talk about this further when there are exceptions to this general trend. But longer times tend to produce higher molar mass than lower times. We know that it has a higher molar mass because it elutes from the GPC, gel permeation chromatography. It elutes faster from the column, which means it has a higher molar mass because its size excluded from the pores. We can also use GPC to help categorize or classify these polymers by examining what happens with copolymers. GPC shifts to higher molar mass with copolymers as well, when we have two independent polymers as we show you here. So we take a look at the GPC of polymer A alone, and we note that it has a lower molecular weight. We note that polymer B, shown in red in this slide, has a higher molecular weight or higher molar mass than polymer A. But when we combine these to make a copolymer, then the AB copolymer has an even higher molar mass than either A or B. So this helps us to classify the polymer and helps us to characterize the polymer. So GPC helps us to categorize these polymers, okay? And therefore, we have an idea of where they might fit for use in use applications, again based upon their molar mass. And we at least now know that their molar mass fits a molecular weight region where they might have utility. So let's go back and recap what we learned about polymeric materials. We know that the physical state and physical properties of the polymeric material are very important to how they are classified. One way they're classified is based upon their solid, liquid, viscosity, or rubbery properties. If they have properties that are more random in its structure, do not have a clear melting point, and are transparent, these features tend to fit an amorphous polymer. So an amorphous polymer has random structure. Crystalline polymers, on the other hand, have more order to them and tend to have a clear melting point and tend to be opaque. Polymer orientation is important to polymer classification. The tacticity can be either isotactic, which means all the backbone, all the groups on the backbone are on one side of the molecule. Syneotactic means they are alternating on either side of the backbone, and but that syneotactic is in an ordered fashion, alternating on the backbone. But atactic is in a random form on the back, alternating on the backbone. We know these polymers, based on the end-use properties, or where we intend to put them into the marketplace, can be either thermoplastics, which means they don't have any cross-links across the polymer chains, or they can be thermosets, which means you have cross-links across the polymer chains. A thermoplastic melts and can be reshaped. A thermoset, heat to its temperature, sets in place and cannot be reformed. Elastomers have great value in the marketplace because of their elastic properties. And that elasticity can be as much as 500 or 1,000 times its original length or original shape, but it always snaps back. There are many applications for this in terms of motor vehicles, consumer products, construction, industry, wire cable, and medical. These polymers may be further classified based upon their monomer distribution. You can have homopolymers, which means that only one type of polymer is there, or you can have copolymers, which means that more than one type of polymer is present. And because of this, certain properties are imparted. Now, these homopolymers can be all A's, they can be all B's. Or the copolymers can be block copolymers, where we have blocks of A and blocks of B. You can have alternating copolymers of A, B, A, B, and it can be in an ordered alternating fashion. Or it can be in a random copolymer. And then again, we can have graph copolymers, where we have one chain of polymer to which a new chain of polymer has been grafted. And again, depending on which of these polymer types or monomer distribution we have, the properties will be defined by them, okay, for in-use applications. These polymers can be further classified or examined based upon their monomers to form the polymers, and they can also be based upon their comonomers to form the copolymers as well. The architecture of these is another way to classify these polymers. We can have linear, which means exactly a straight chain, branch, straight chain with random groups off the side, star polymer, having at least 3 or 4 different polymer units off of a hub. Rake would be a linear with branches hanging down it. And what we find is that about 75% of the market will fit into these categories. Okay. Then there are others, however, okay, that are thermosets, would involve things such as a network, which is a more crowded or randomly shaped polymer, which a lot of intertwined connections. And then you can have these ladders. And again, many of these would be thermoset type materials. You have phenolics, for example, and epoxies are examples. And then we can also further characterize or classify polymers based upon the commercial applications. And each commercial application has a recycling code associated with it to help determine how it might be reused or landfill or properly disposed of. We have these classifications because we have these monomers we choose. These monomers are polymerized into oligomers, which are intermediate chain polymers, small chain polymers, are further polymerized into 1,000-unit monomers, what we call a full polymer. And those full polymers, again, homo, block, alternate, random polymers, may be further classified based upon their GPC analysis, whereby larger molecular weight polymers come out first in the GPC, smaller molar mass polymers come out later in the GPC because they enter the pores. Smaller polymers enter the pores and more surface area there, and they lag in terms of their time of elution from the GPC. This is the case for block copolymer in groups or in blocking. This is also the case for where we have examination of the extent of polymerization, where the longer, in general, rule of thumb is the longer we polymerize, the more polymer we make. This is also the case when we take A polymer and B polymers, combine them, make copolymers. The copolymer has a higher molar mass. And that completes Chapter 2, Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis.